Good morning, everyone. Today I want to talk to you a classic digital circuit design problem. Here is the problem. We have a sequential circuit with two flip-flops, A and B, one input called X, and one output called Y. The state diagram is already given to us. You can see it on the slide right now. Our job is to implement this circuit using the flip-flops. But here is a twist. Instead of the usual binary state encoding, we will use something called one-hot state assignment. By the time we finish, you will see that one-hot encoding lets you write the circuit equation directly by reading the state diagram. No cap, no maps, no truth table minimization, just straightforward logic reasoning. Let us get started. Before we touch any equation, the very first thing we need to do is identify what type of sequential machine we are looking at. Take a look at the state diagram. Notice where the output Y is written. It appears inside each state bubble, right next to the state label, separated by a slash. For example, you can see state 00 written as 00/1, meaning the state is 00 and the output is 1. This placement is a key clue. When the output is written inside the state bubble, the output depends only on the current state, not on the input. We call this a Moore machine. For comparison, if the output were written on the transistor arrows, instead of inside the bubble, it would depend on both the current state and the input. The type is called a Milli machine. In this problem, we have a Moore machine. Now we take the state diagram and read every single transition out of it. Then we call them systematically in a state table. We have 4 states, 00, 01, 10, and 11. I will refer to them as S0 through S3 for convenience. For each state, we ask two questions. What happens when the input x equals 0, and what happens when x equals 1? Reading directly from the diagram. State S0, which is AB equals 00, when x equals 0, the machine moves to S1. When x equals 1, the machine stays at S0. This is a self-loop. The output y equals 1. State S1, AB equals 01. When x equals 0, it stays at S1. Another self-loop. When x equals 1, it moves to S2. The output y equals 0. State S2, AB equals 10. When x equals 0, it moves to S3. When x equals 1, it stays as S2, a self-loop. The output y equals 0. State S3, AB equals 11. When x equals 0, it stays as S3, a self-loop when x equals 1. It goes back to S0, the output y equals 0. Now look at the output current. Y equals 1 occurs only in state S0. Every other state produces y equals 0. This is exactly the Moore machine behavior we identified. The output is determined entirely by which state we are currently in. Now, here is where the technique becomes interesting. Instead of encoding our flow state in binary, which will only require two flip-flops, we are going to use one-hot encoding. In one-hot encoding, we dedicate one flip-flop to each state. With 4 states, we need 4 flip-flops. I will call them Q0, Q1, Q2, and Q3. The rule is simple. At any point in time, exactly one flip-flop equals 1. All the other equals 0. Whichever flip-flop is currently holding a 1 tells you which state the circuit is in. The assignments are: state S0 corresponds to Q0 equals 1, and Q1, Q2, Q3 all equals 0. The one-hot code is 0001. State S1 corresponds to Q1 equals 1. Code 0010. State F2 corresponds to Q2 equals 1. Code 0100. State S3 corresponds to Q3 equals 1. Code 1000. Now you might be wondering, we have 4 states and binary encoding only needs 2 flip-flops. Why are we using 4? The answer is that one-hot trending more flip-flop from much simpler equation. The payoff arrives in the very next step. This is the heart of the entire design. Let me state the key rule for one-hot design. For each flip-flop Qi, the D input equals the O of every condition that causes the machine to enter state Si on the next clock edge. In other words, look at the state diagram and find every arrow that points into state Si. Each arrow contributes one product term. The source state ends with the input condition, or all those product terms together, and you have the equation for Di. Let us go through each one. D0, we want to find every transition whose destination is S0. First, the machine is already in S0, meaning Q0 equals 1, and the input X equals 1. Each state at S0, this cell would contribute the terms Q0 times X. Second, the machine is in S3, meaning Q3 equals 1 and X equals 1. Each transition back to S0, this contributes Q3 times X. We add these two terms together. D1, every transition whose destination in S1. From S0, when X equals 0, Q0 times X prime. For S1 itself, when X equals 0, a subgroup Q1 times X prime. D2, every transition whose destination is S2. From S1, when X equals 1, Q1 times X. From S2, when X equals 1, a subgroup Q2 times X. D3, every transition whose destination is S3. From S2, when X equals 0, Q2 times X prime. From S3, when X equals 0, a subgroup Q3 times X prime. D3. Before we move on, notice the beautiful pattern in these 4 equations. D0 and D2 are iterated when X equals 1. D1 and D3 are activated when x equals 0. Every equation consists of exactly the subroutines plus one incoming. There is no coincidence. It is a direct consequence of the structure of this particular state diagram. The output equation is almost embarrassingly simple, and that is entirely due to the Moore machine structure, because the output depends only on the present state. We just look at the state table and ask, in which state is y equal to 1? The answer is only in state S0, which corresponds to Q0 equals 1. In every other state, y is 0, so the output equation is simply y equals Q0. Before we move on, I want to stress a distinction that trips up a lot of students. The D inputs we just derived, D0 through D3, come from the next state. They represent what the flip-flop should hold after the next edge. But the output Y comes from the present time. It reflects what the machine is doing right now before any clock edge occurs. The input comes from the next state. Output Y comes from the present state. These are different time references, and mixing them up is one of the most common mistakes in sequential circuit design. Let us bring everything together. Here are the 5 equations that completely and fully define the sequential circuit. 4D flip-flop for next state equation, 1 output equation, and we derive all of this purely by reading the arrows on the state diagram. No Carnot maps, no truth table minimization, no algebraic simplification required. A good engineer always verifies. Let us trace through one example step by step to confirm that our equations are correct. We start in state S0, that means Q0 equals 1, and Q1, Q2, Q3 all equals 0. The input x equals 0. Let us plug this value into every equation. After the clock edge fires, the flip-flop loads their D values, so Q1 becomes 1, and everything else becomes 0. That is state S1. Let us check against the state diagram. The diagram says from S0, where x equals 0, go to S1. That is exactly what our equation produced, and y equals 0 because we were in S0 also correct. The equation checked out, you can verify any other transition from the state diagram in exactly the same way. There are key concepts and common mistakes in this problem. First thing, D inputs equals next state. Second thing, no Carnot map for 1 hot. Third thing, D depends on next state. Y depends on current state. Fourth thing, 1 hot assumption and initialization. These are all the circuit design steps for this problem. You can stop and look at them carefully. That's all for today. Thank you for listening.